Hi, and welcome to Mike Likes Robots, where we share knowledge to accelerate robotics. And today, I've already completed day 17. So over the past few days, the puzzles have been getting steadily harder. I've not been able to complete them in time or even get anywhere near to completing them in time. So from now on, what I'm going to try and do is complete them ahead of the video, then read out the puzzle and take you through what my code does and where I went wrong in trying to implement my solution. I hope it's still interesting to you. Please let me know in the comments if you do want to see the start out of me trying to code and my initial thoughts in trying to solve the problem. Otherwise, I'm going to read out the puzzle. There'll be chapters in the description if you want to skip ahead. Day 17 is called Chronospatial Computer. The historians push the button on their strange device, but this time you all just feel like you're falling. Situation critical, the device announces in a familiar voice. Bootstrapping process failed. Initializing debugger. The small handheld device suddenly unfolds into an entire computer. The historians look around nervously before one of them tosses it to you. This seems to be a 3-bit computer. Its program is a list of 3-bit numbers, 0 through 7, like 0, 1, 2, 3. The computer also has 3 registers named A, B, and C, but these registers aren't limited to 3 bits and can instead hold any integer. The computer knows 8 instructions, each identified by a 3-bit number called the instruction's opcode. Each instruction also reads the 3-bit number after it as an input. This is called its operand. A number called the instruction pointer identifies the position in the program from which the next opcode will be read. It starts at 0, pointing at the first 3-bit number in the program. Except for jump instructions, the instruction pointer increases by 2 after each instruction is processed, to move past the instruction's opcode and its operand. If the computer tries to read an opcode past the end of the program, it instead halts. So the program 0, 1, 2, 3 would run the instruction whose opcode is 0 and pass it the operand 1, then run the instruction having opcode 2 and pass it the operand 3, then halt. There are 2 types of operands. Each instruction specifies the type of its operand. The value of a literal operand is the operand itself. For example, the value of the literal operand 7 is the number 7. The value of a combo operand can be found as follows. Combo operand 0 through 3 represent literal values 0 through 3. Combo operand 4 represents the value of register A, 5 represents B, 6 represents C. And 7 is reserved and will not appear in valid programs. Now, my thought here is that it's either for part B or for a future puzzle, so we should probably have a way to preserve the computer for future iterations if we need to. Anyway, the 8 instructions are as follows. The ADV instruction, opcode 0, performs division. The numerator is the value in the A register. The denominator is found by raising 2 to the power of the instruction's combo operand. So an operand of 2 would divide A by 4, 2 squared. An operand of 5 would divide A by 2 to the B. The result of the division operation is truncated to an integer and then written to the A register. The BXL instruction, opcode 1, calculates the bitwise XOR of register B and the instruction's literal operand, then stores the result in register B. The BST instruction, opcode 2, calculates the value of its combo operand modulo A, thereby keeping only its lowest 3 bits, then writes that value to the B register. The JNZ instruction, JNZ for the Americans among you, which is opcode 3, does nothing if the A register is 0. However, if the A register is not 0, it jumps by setting the instruction pointer to the value of its literal operand. If this instruction jumps, the instruction pointer is not increased by 2 after this instruction. The BXC instruction, opcode 4, calculates the bitwise XOR of register B and register C, then stores the result in register B. For legacy reasons, this instruction reads an operand but ignores it. The OUT instruction, opcode 5, calculates the value of its combo operand modulo 8, then outputs that value. If a program outputs multiple values, they are separated by commas. The BDV instruction, opcode 6, works exactly like the ADV instruction, except the result is stored in the B register. The numerator is still read from the A register. The CDV instruction, opcode 7, is the same but stored in the C register. Here are some examples of the instruction operation. If register C contains 9, the program 26 would set register B to 1. If register A contains 10, the program 505154 would output 012. If register A contains 2024, the program 015430 would output 42567777310 and leave 0 in register A. If register B contains 29, the program 17 would set register B to 26. If register B contains 2024 and register C contains 43,690, the program 40 would set register B to 44,354. So lots of examples here to make sure you're writing the correct code. The historian's strange device has finished initializing its debugger and is displaying some information about the program it is trying to run, your puzzle input. For example, register A has 729, register B has 0, C has 0, and the program is 015430. Your first task is to determine what the program is trying to output. To do this, initialize the registers to the given values, then run the given command, collecting any output produced by out instructions. Always join the values produced by out instructions with commas. After the above program halts, its final output will be 4635635210. Using the information provided by the debugger, initialize the registers to the given values, then run the program. Once it halts, what do you get if you use commas to join the values at output into a single string? Now, I did solve this. When I first read through, I had some trouble figuring out everything. There was just a lot of information to determine how to run the puzzle. When it came to actually writing the code, it was fairly simple. So the next thing I'll do is show you the project where I build the computer and how I manage the parsing, the combo lookup, and the instruction management. So I started with a main function and immediately decided to make a computer module to keep all of the code in. It turns out that this is the only module I ended up using. Nevertheless, I've got it here. So let's take a look. The computer turned out to have 3 registers, A, B, and C, and a program with a vector of U64s. So that would be the individual digits of the program. I started out by using U32 to encode everything. I then had to update to U64 for reasons I'll go into later. There's also the ability to clone, which I tried to derive and I don't think it worked, but when I did it manually, that meant that I could clone the computer to be able to run from a single starting point. The trouble is that because you're modifying registers, to do it immutably is quite challenging. It's much easier to write it mutably, but have a clone function so that you can clone the computer before running operations on it, so that you've still got your original program without having to reparse the text file. The next step was to do the from string. So I am certainly looking for any advice on how to make this neater, because I think what I've done is not very pretty, honestly. I think I could have done this in a better way. So for A, B, and C, I think you could just, in another program, let's say Python, I would split by colon. I would take the second value, so index 1, and I'd pass it as an integer. And that would just be like int of dot split colon, for example. So it'd be really, really short. What I've got here is not really, really short. I have to take the 0th and the first and the second line, and for each one, split by white space. I map each segment to I try to parse each segment as a U64. I find the first one that works, and then I unwrap it or give it a value of 0. So if there's an invalid number in here, let's say it's FJD, it will still give me 0. But I probably shouldn't have that because that's an invalid computer at that point, right? It means something's gone wrong with the file. Moving on, the program is similar. It splits by white space, takes the first entry, meaning this batch of numbers, splits by comma instead, so that we've got the individual digits and then parses each one as an integer. So fairly simple, and it gives me back a computer. Okay, moving on to the get operand function. So because we've got this combo operand, right, 0 through 3 is literal value 0 through 3. So when we are using the program, this get operand, you want to look up what the operand is. If it's 0 through 3, it returns just the operand. If it's 4, 5, or 6, it returns A, B, and C, respectively. And 7 is reserved. Anything else gives you none, which is why this function gives you back an option. There's so many possibilities you can pass in. For correctness, I made it return an option. But wherever I use it, I just .unwrap it. Moving on, past all these comments, that will help with the part 2 explanation. So here's the actual program code itself. So I wrote a tick function, which you repeatedly call. What it does is returns the new, the puzzle called it instruction pointer. I'm used to calling it a program counter, so I keep using PC. So when you see PC, think program counter, or think instruction pointer, whatever your preference. So this function will return the next program counter to move to, and if there's an output, it will give that output. Some of the output if it's there, or none if there's no output. So then you can repeatedly call this code until your new PC is past the end of the program. That's exactly what part A does, which is here, called self.getOutputs. And then self.getOutputs will start PC at 0, it'll keep a vector to store outputs in, then it repeatedly gets the new program counter from the tick function, sets the current program counter to the new program counter, and if there was any output, it pushes it into the outputs vector. By doing that, I can then iterate over them, convert them all into strings, and join them together with commas, which is what produces the final output. So going back to the tick function, I can now look at all the different opcodes, and what I did basically was copy out all of the instructions from the document, the puzzle document, so that I could write each one in turn. Now, probably a lot of them are pretty self-explanatory, like jump not 0, check if A is 0. If it's not 0, then return the next return the next number in the program, which is the operand, as the new program counter. If I have to do something with a combo, let's say I'm setting B to the bottom 3 digits of the combo, then I can use self.getOperand for the next number in the program, and then bitwise AND it with 0x7, which is also the binary digits 111. So it's pretty helpful to understand binary and bitwise operations for this puzzle. They come in, they are used very heavily. Other things that are interesting, the only other thing that's not very obvious is this bit shift. So when the puzzle talks about the numerator and the denominator and then truncating the integer, this is equivalent to a bit shift. So let's say I have my numerator, it's the value in the A register, that's pretty simple. The denominator is found by raising 2 to the power of the instruction's combo operand. So let's say we've got the literal value 2, we're trying to divide by 2 squared. That is equivalent to right shifting by 2 places. So we don't need to calculate 2 to the power of something, and we don't need to truncate. All we have to do is bit shift by whatever the value is that we're trying to calculate the denominator from. For 2, we bit shift by 2. If we're using the value in register B, we bit shift by the value in register B, and that's it. And that is the same for the BDV and the CDV instructions. It's just a bit shift by a particular amount. So back in the main function, I can now run this, and it simply gives me this string as an output by joining together all the values in the out. So this part A was pretty simple, and I was feeling somewhat confident as I completed this. I put it into the puzzle. The puzzle answer was correct, and so I went on to part 2. So now I'm going to read through part 2. Again, chapters are in the description. Please skip ahead if you don't want to hear the puzzle. Part 2. Digging deeper in the device's manual, you discover the problem. This program is supposed to output another copy of the program. Unfortunately, the value in register A seems to have been corrupted. You'll need to find a new value to which you can initialize register A so that the program's output instructions produce an exact copy of the program itself. For example, register A has 2024, B and C have 0, and the program has changed. It's now 035430. This program outputs a copy of itself if register A is instead initialized to 117,440. The original initial value of register A, 2024, is ignored. What is the lowest positive initial value for register A that causes the program to output a copy of itself? So you can see that I've got the answer here already, and I'll go through how I found it, which was not immediately obvious. Now, the first thing that I tried to do was pretty naive, and I knew it was naive while I did it, but I wanted to see just how bad it was and make sure that I was writing the code correctly. So instead of get outputs, I wrote this part B function. So what this part B function did was save the original B and C values from the B and C registers. Then it searches from 0 upwards, that's its 0 ... and looks for the first candidate A from 0 onwards that satisfies the following function. I've got a print line for debugging. I set the A register to the candidate, and then I reset the B and C values in case they've been updated. So the point here is that I'm not cloning the computer to do it. I'm changing the A value and I'm changing the B and C value. The program never changes. As I'm always throwing away the A value, I can set the new A value and reset the B and C values to whatever their initial values were, and then it's a clean run. Then I use the function self.produces own program. This produces a Boolean value. All it does is says, run the simulation, and if it outputs the same program as its input program, then it produces its own program. It returns true. So my initial attempt at this was that I ran the part A function. That's why it's in a separate getOutputs function, even though I don't use it anywhere else. So I run the getOutputs function, and then I check if that's the same as comma joining all of the inputs from the program. I did that, and it started calculating and took a long time, and I decided it was time to start optimizing. One way to optimize, I decided, was to copy the outputs that I was expecting, and then repeatedly check. For every new output that appeared, I would check if it's the output I'm expecting. So what this should do is stop calculation of the program early if it's not matching the output. So instead of waiting for the entire output to be calculated, it calculates the first value and checks it. Then it calculates the second value and checks it. Now, this made it run probably slightly faster. I didn't measure. In theory, it should. The problem is that, as you'll see from the actual final output, running from 0 onwards was just taking far too long. It was time to actually think about the problem and try and solve it deliberately instead of throwing numbers at a computer and hoping that something falls out. So then I started thinking about how to solve the problem, and this is where all the comments on the page come in. I decided to try and reverse engineer the program, and my instinct was right, this is exactly what I needed to do. So I needed to figure out everywhere that the program used register A. I checked that the program counter is always even by running the simulation for a while and telling it to panic if it was ever odd. It never was, so I can always assume that the program counter is odd. There's actually nothing in the coding that stops it from setting the program counter to odd, as long as it can then reset to even in order to finish the program. In fact, it doesn't even need to reset to even to finish the program, it can just keep going. So I checked that it's always even, and it is. So I knew that I can always interpret the program in order. From this, I was able to figure out from the test text exactly what the program did. Now, an interesting part is that initially I didn't realize that there was a new test text. The puzzle has this example, which has 015430, and then this example, 035430. And it took me a while to realize that those two are different. So for a while, I was running with the wrong input program. After a while, I realized that that was the case, and I started translating this program. So let me translate this so that you can see what's happening. You can see my thought process here. So 03, if we look in the computer, 0 will take A and right shift it by whatever is in the next slot, which in this case is 3, right? 0, 3. So because 3 is the literal value, it takes A, shifts it right by 3, and saves it back to A. So we immediately know that, yes, I've written 1 here because I started reverse engineering test, and that has 1. So this should actually correctly be 3. Then it goes to 5, 4. So what 5, 4 does, 5 is the out command. So it prints out whatever is in the operand here. Because it's 4, 4 corresponds to register A. So it outputs A, or rather it outputs the bottom 3 bits of A. Then it does 3, 0. 3, 0 is jump if A is not 0. So jump to 0. Basically, go back to the start if A is not 0. So from that combination, we can rewrite this program into some pseudocode while the value in register A is greater than 0, not equal. While it's greater than 0, shift it right by 3 places and then print out the bottom 3 bits. So that's what the program does. From that, I could figure out how to calculate the value of A that would make it output its own program. And I've written it into the solve test text function. Now, one note here is that I don't know if there's a way to reverse engineer any program that goes in to find a value of A that does its own thing. I've coded it manually very specifically to the algorithm I'm trying to solve, which is why I have separate functions for solve test text and solve input text. In this case, I set the accumulator to 0. I go through all the digits in the program in reverse, and then I figure out, or rather, I just encode the 3 bits into an accumulator, I've called it. So it sets the accumulator to the digit, the bottom 3 digits of the accumulator to the digit I'm trying to solve, and then shifts the accumulator along. By doing that, the accumulator will keep shifting along for as long as there are digits in the program. Another thing to mention here is the bitwise operation going on. This line of code, what it does is it takes the accumulator, it does the bitwise inverse, or bitwise not of 111. 0B111 is the binary digits 111, right? By doing the bitwise not, that's 000, except that we're using 64-bit numbers. So it's not 000, it's 11111111 all the way down to 000. By doing that, we do a bitwise AND with the accumulator. So the effect of that is that it keeps all the bits up to the last 3 digits, and it sets those 3 bits to 0, because AND with 0 is always 0. Then we do a bitwise OR with the digit. Now the digit I've assumed here is always 3 bits, or encoded within 3 bits. Technically speaking, I could wrap this in AND 0B111 just to make sure, but it always is, so I don't need to. So then it's setting the bottom 3 bits to whatever the digit is. So that's the value. This piece of code here sets the bottom 3 digits to the value that I'm trying to set. Then it shifts it along by 3. So that's the left shift operator. So that's how it works. And when I ran this, it correctly solved test text. In fact, I think I've encoded it in a unit test. So solving cargo test shows that I was able to reverse engineer the test text and find the value of A that caused it to output its own program. Great. The trouble is that the input text gets a little bit more complicated. The value of input text, I won't go through the program, suffice to say that this is what it means. While RA is greater than 0, the value of RB is the value of RA, or rather the bottom 3 digits of it. Then you XOR it with 1. So you're flipping the bottom bit of RB. Then you get the value into C of the value of A shifted right by the value of B. This actually threw me for a while because I mistranslated this as 5 meaning the value in register B, and I interpreted it as the literal value 5, which is wrong. So that's another point that I messed up the code a bit. Then RB is saved to the register value B, XORed with the register C. Then register B is XORed with 100, right? So it's flipping the third bit. If you're using 0 indexes, it's bit 2 from the right. Then RA gets shifted right by 3 bits, and then it outputs whatever is in value B. So this did mean, when I looked through it, that I figured out RA would need to be a number at least 1 shifted left to the program length times 3, right? Because it's constantly shifting right by 3 and outputting the number. If you take the program length, which was 16, it would need to be at least 1 shift left by 48. And I realized that that doesn't fit inside a U32, which is what I originally used, right? A U32 is a 32-bit number. You can't shift a number right or left by 48 bits and have it fit within a 32-bit number. It's just not big enough. That's when I changed all of the numbers in the code to use a U64. Then I tried to reverse engineer this a bit. I just compacted the program down a bit to make it a little bit easier to read. It ended up not helping that much, but that's why it's there. And then I started trying to solve it in a similar way to how I solved test text. And what I realized, or rather my theory, and feel free to correct me in the comments if this is wrong, is that there is, I have to guess what B is and then check if it works correctly. So my original algorithm was that I would try and reverse engineer it. I'd do it backwards. So I had the program, I set B to the digit and then I flipped bit 2, and then I calculated what RC was, which was RA shifted right by 5, I thought, but it's register value B, which made it a lot more difficult. If it was a constant number, it would have been simpler, but because B varies, it wasn't as simple. And then, of course, you also have to XOR with 1, and then insert it into register A. Now, I realized by doing this that I didn't know what the value B was, so I started using a for loop, B from 0 to 7 inclusive. For each one, it would test whether that value of B worked for the program. So this program here is essentially this program here. You take the value B, instead of looking it up from A, we figure out what we want it to be, and then we XOR it with 1. We figure out that C is the accumulator, or register A, in this case, shifted right by B. That's here. B is XORed with C, like this. Then it's XORed with 100, like this. Then I want to keep only the bottom 3 bits, right? So out RB and that, and I also want to set it. So if that turns out to be the digit I want it to output, then save it into the accumulator. But even this, when I ran it, was producing the wrong values. And the reason was that because C changes as the value of B changes and as your accumulator grows bigger, I'm not sure if there's a deterministic way of solving this. So instead, what I did was save all the values of B, or rather I checked if there were multiple values of B which worked. Instead of trying to skip this loop, I originally had this, and if B was digit, then I would continue outer. As a kind of optimization, I found a value of B that works, save it, and let's move to the next digit in the program. That didn't work. Instead, I started saving all of the possible candidates for register A, or accumulator as I'm calling it, that could solve the problem. So after this, I end up with a vector of possible accumulators which fit these rules, but only one of them produced its own program as an output. So at that point, I started trying to test it. And the way I tested it was by cloning the computer, setting the candidate to the value in A, and then running the producer's own program. I actually don't need this because this was a debug code to help me figure out where it was going wrong while I was still making it. So if it turned out to produce its own program, then return that candidate. So I think it was about 16 or so accumulator candidates that I ended up having. So 8 occasions, I believe, or maybe it was 4, and then it was 4 times 4. Anyway, I'm guessing at numbers here. Roughly 4 times where there were multiple values of B that could have worked for the accumulator. After doing this, and I was very confused at why this wasn't working, I realized that by always shifting left by 3 here, I was actually producing an accumulator that was too large. So just at the end of the loop, after they'd all been computed, I took it down 3 steps again. So all the accumulator candidates shifted right by 3 to get it down to the right size. And I realized that by printing it out and realized that they all produced, or rather one of them produced the program output, but with an extra digit on the end, so that the comparison failed. So by shifting it right by 3 digits, I was able to get the actual accumulator values, which might have worked. And then I tested them all and found one that worked. So again, I don't know if there's a deterministic way of doing this without testing different values of B and without keeping a track of which candidates work and which don't. But for me, this works, and it works very, very fast. So I can show you it running now. I need to reset this line so that it keeps it. Cargo run in release, and straight away it produces the output number here. So that's how I solved it. That's some of the issues that I had along the way. That is day 17 complete. Thank you for watching. Let me know if you prefer the format of this video. I know it's much smaller, but you don't get to see as much coding, and I'd like to hear from you if it works. So thanks for watching, and I will see you in the next video.